This week, Jesse Michael, principal researcher at Eclipsium, joins us to talk about UEFI and SMM vulnerabilities. In the security news, stealing Mastodon passwords, reporting vulnerabilities in open source privately, labeling does not solve problems, or does it? Will it ever get patched? Geolocating people from photos, no metadata required. Update your firmware on Linux. Hacking flow computers. When a driver isn't really a driver, well, it's a driver, but maybe not the one you're thinking of. Oops, I leaked it again. Misconfiguration leads to compromise. Hardened runner, guard dog, and hacking spacecraft via Ethernet. All that and more on this episode of Paul's Security Weekly.
This is Security Weekly, for security professionals, by security professionals. Broadcasting live from G-Unit Studios in Rhode Island, it's the show where exploits run wild, packets aren't the only things getting sniffed, and the cocktails flow steady. It's Paul's Security Weekly.
Right now, everybody is talking about cryptocurrency, and the cybercriminals are hiding in the conversation. Cybercriminals use social engineering, loaded with urgency and fear, to successfully prey on your company, your employees, and your customers. Spear phishing is just one of 13 types of email threats. Barracuda has identified these 13 types and shows you how you can protect your company, your customers, and your reputation. Find out about the 13 email threat types and Barracuda email protection. Get your free ebook at securityweekly.com/Barracuda. That's securityweekly.com/Barracuda.
And welcome to the show. But first, let me introduce you to a man who poop jokes aren't his favorite, but they're a solid number two, Mr. Paul Asadorian.
Welcome, everyone, to Paul's Security Weekly. It's episode number 764, recorded on November 16th, 2022, right here in G-Unit Studios in Rhode Island. To my left, Mr. Larry Pesce.
Yeehaw.
And now, becoming a regular fixture here in the studio, Mr. Jeff Mann has joined us.
I'm
in
back,
person.
Yes.
Nice having you here.
And I coordinated so I'd be here a week that Larry was here.
I know, that's
We
awesome.
miss each other.
It's amazing. It's good to have you both here in
I
studio.
miss you too, Paul.
If you guys would go to the range more, you'd stop missing each other.
That's right. Mr. Dad Joke tonight, Mr. Josh Marpet is here with us. Josh, welcome.
Happy to be here as always.
Mandy the Pirate Logan is here with us. Mandy, welcome.
Why, thank you. And I like hacking sandwich making through Ethernet.
Sandwich making.
Sandwich making. Do you need to use sudo first?
I think you need a pseudo vulnerability for that, right?
Yeah.
That was good. That was good.
Tyler Robinson is here with us. Tyler, welcome.
You guys are on it today.
Today? Come on now. Mr. Sam Bound is here with us. Sam, welcome.
Good evening. Glad to be here.
I think I got everyone, right? Okay. Join our Discord channel to chat with our host, ask questions, customize live stream alerts, and more. Visit securityweekly.com/Discord even to receive an invite. That's Discord. Please join me in welcoming Jesse Michael, principal researcher at Eclipsium, also one of my coworkers. Jesse is an experienced security researcher focused on vulnerability detection and mitigation, who has worked at all layers of modern computing environments, from exploiting worldwide corporate network infrastructure down to hunting vulnerabilities inside processors at the hardware design level. Jesse, welcome to the show.
Great. Glad to be here.
Jesse also is going to probably say it depends, like at least six times. Jesse and I have these conversations at work all the time, and I ask
probably
Jesse,
yes.
I'm like, Jesse, I'm trying to understand this. I'm like, I have this question, and he's like, well, Paul, it depends. I hear that a lot. And now I feel like you're an expert witness, because I want to get your background, what qualifies you, Jesse Michael, to talk about UEFI and SMM. But how did you get your start in information security, Jesse?
In information security in general, I've been doing this for probably longer than I should admit. I started off doing.
Do you remember the turbo button on the front of the computer?
Yes, yeah.
So there you go. You've been doing it a long time.
No, so I started off in kind of doing QA, and then I moved into security software, reverse engineering, writing exploits, and then I went and worked for Intel for a number of years. And as part of that, I basically was, as you just mentioned, I was literally looking inside the processors, inside the chipset at the Verilog design level, looking at a lot of these different interactions in the system, at the internal microarchitectural level as well as the architectural level as well. And as part of that, I also spent some time leading a security team for BIOS within Intel, and helped work with the product teams to improve their security practices. So I do have some experience with working at
Jesse,
a lot of these low-level components.
Yeah, but when you say BIOS, you mean like pre-UEFI BIOS?
Yeah, so the BIOS is basically the old version of what's now UEFI. Back in the old days, when like the x86 and IBM PC first came out, we had BIOS, basic input-output system. It's basically the firmware that runs on the system and is built into the computer that then finds the operating system, loads that, and starts the whole process of booting up the system and getting it running so you can actually use it for useful tasks. But it had a lot of limitations, and as people were running into some of these limitations when they were making servers and other things, Intel started a initiative that initially was Intel Boot Initiative, and then they renamed it to EFI, Extensible Firmware Interface, and then they expanded that and basically took the spec that they were producing for this EFI environment and mechanism for launching the system, and helped create what's called the UEFI forum for unified EFI, Unified Extensible Firmware Interface. And then the UEFI forum creates the spec, and then there are implementations, but it basically is the new version of that firmware that is built into your computer. In general, there's a SPI chip on the motherboard that contains the code that runs when the system powers on. There's a lot of things that
Jesse.
happen. Yeah, sorry. Go ahead.
Yeah, well, Jesse.
I get into a lot of details there, so totally stop me when you
Jesse
need to.
and Mickey, I mean, you guys have done like days-long training on this stuff too, and we're trying to cram into an hour. And Jesse and I were already like, this is going to be hard, right? So, but UEFI was developed like right up to 2011. I forget the exact dates, right? But it almost doesn't matter because 2011 is where we started seeing adoption. Just so people know, like when I have a computer, if it was after 2011, it was Intel based. You probably have some kind of UEFI.
Yeah. So one of the things that helped drive adoption of UEFI is that for Windows 8, when Windows 8 came out, one of the features that was added as part of UEFI is this concept of secure boot and doing things like cryptographic signature verification of the code that's being loaded before it runs, so that you can actually trust that the thing that you're running on your system is what you expect to have running. And so secure boot was added to UEFI. That didn't exist in BIOS before. There was no security there, so we had a lot of things like boot viruses and that type of bootkit. UEFI added secure boot, and then Microsoft required secure boot to be enabled in order for a system manufacturer to put the Windows 8 logo sticker on any systems that they were shipping. So
I didn't know that was like the initial kind of driver for that.
No, that was one of the things that helped get more adoption with the different OEMs, is that it was a specific logo sticker requirement for Windows 8 in order to support secure boot. So you did have the ability to go into BIOS and turn off secure boot if your operating system didn't support that. But in general, most systems shipping after 2009, 2010, 2011 generally will support secure boot. There were some servers that shipped and didn't support secure boot for a little while longer, just because servers were a little bit slower to adopt some of these technologies. But in general, if you go to the store, buy a laptop, something that'll run Windows, it'll generally support secure boot.
And there's a lot more going on in UEFI than, I mean, secure boot's just one thing. And there's a slide that we have to include every time we talk about UEFI. That's the stages of UEFI, and I think that's like the torture test at Eclipsium. They're like, well, you have to put this in your deck and be able to explain it, kind of thing.
Just about, yeah.
I mean, we could spend hours talking about all of the phases of the boot process in a UEFI computer, is there a high level specifically? I think I have some questions about DXE given the latest Lenovo vulnerabilities too. Jesse, it's kind of time.
Yeah, there are a few major points or stages where these are running. Where the very first code that runs at the reset vector, basically the CPU comes out of reset, it starts executing code. That's essentially a phase that's called sec or security. It's doing some very early initial setup to do things like switch. So when the CPU boots up, it still comes up in essentially 16-bit real mode, even in 2022, which is kind of crazy to me because of all the backwards compatibility in these processors. But this first phase will do things like switch into protected mode, 64-bit, and set up some of the memory protections and enable memory. So
and those are
it does some of that really low-level hardware things.
Sorry, real mode, protected mode, and system management mode are all modes of the processor. We should probably back up because that's kind of where I want to steer the conversation to. And I stepped on Tyler twice already, so I want to make sure Tyler asks his question as well. But just, I guess at a high level, just like modes of the processor, because we mentioned 3 now already.
Yeah. So there are different modes in this processor. So in Intel architecture, there's something called real mode, which is the old style, essentially 16-bit addressing with segments, and nobody really uses that anymore other than in this initial setup. And then there's also this concept of protected mode where you have paging and page tables, and that's generally the mode that things are running in once you're actually up and running a modern operating system. But there's also this mechanism called system management mode, which it originally came out in, I think, 1990 or so. So it's been around for a long time. But even in a modern operating system or modern CPU in 2022, when you're running a full 64-bit operating system, system management mode is still running in this 16-bit mode, but it has the ability to go and access other things. The interesting thing about system management mode is that it is a more privileged mechanism in the processor. So normally what you think of is the system boots up, it loads the operating system runs, and you have kernel mode and user mode. And there's a mechanism in the CPU that a lot of people have heard of, which is called rings. And you have like ring 3 and ring 0, where ring 0 is essentially kernel mode and ring 3 is user mode. There are some small, less common operating systems that will run drivers in like ring 2 or ring 1, but generally modern operating systems like Windows and Linux will just use ring 3 for kernel, which is more privileged, and ring 3 is less privileged for user applications. But above and beyond this mechanism that the operating system is managing is this thing called system management mode, which is actually more privileged than the operating system itself. So when the operating system boots up, the kernel is running. If the system has been set up correctly and some configuration made, there's an additional memory region that even the kernel running with full administrator kernel privileges doesn't have the ability to look into this particular area, which is called system management RAM. And it's basically it's part of your main system memory, but it has some additional protections that the CPU enforces to allow any reads and writes into that.
I'm gonna let Tyler go because he's been trying to ask a question for like since we started.
No, I was just curious. Is that considered like ring -0 then, where SMM runs, or is that actually like below ring -0?
So a lot of people will use like negative rings. I tend to not really like that type of framework. It's more of like a general concept that there aren't really negative rings in the CPU. There are just rings 0 through 3, but then there are some more privileged mechanisms like virtualization. If you have virtualization hardware active, you have the hypervisor, which is more privileged than the guest, but that guest is then running in ring 0 code. So conceptually, you could think of it as like ring -1 or something. But there's also
Are those
system
privileges
management
or
modes.
identities, or are they just known functions that have the permissions within inside of given regions of hardware? Like, are those all separated and kind of mapped out to, again, a role, a group, an identity? Like, how would you conceptualize that at that low level?
That's a great question.
Not really like like if you're thinking of like user authentication or something like that, it's not really a mechanism like that. It's basically there's something called a system management interrupt. So like when you're in to kind of think about it in terms of like an operating system, when you're in when you're running in a user application, there are mechanisms for transferring between user space and kernel space and changing the mode of the processor. So to go from a user application running in ring 3 to a kernel service running in ring 0, the processor goes through what's called a mode switch, and it does some things for you at the microarchitectural level that are then exposed in architectural ways. And there's a kind of a distinction between microarchitectural internal things that we don't really have good public documentation about, versus if you read the Intel Software Developers Manual, which is like 70 meg document, which is thousands of pages. That's all the architectural explanation of how this works. But it does a lot of these things to switch modes, and then there's similarly a mode switch operation to go from running in the kernel or even in ring 3 to trigger what's called a system management interrupt. And when a system management interrupt happens, it basically the processor will save the state of the system in a particular part of RAM inside of this protected region of memory, and it'll
Jesse, that's
it'll
usually,
then
is that usually the first 16 megabytes or gigabytes? How big is the because UEFI actually creates this, like the code in UEFI creates this special area in RAM, correct? And it's a certain size usually.
When the processor is booting up, I got to the sec phase that we started talking about, but
there's a lot to unpack.
After that, there's a pre-EFI environment, and then Dixie driver execution environment is the largest phase, and that's running most of your drivers and applications. After that, there's boot device selection, which is what's going out and finding your bootloader, transitioning and running the bootloader, and then the bootloader then loads and runs the operating system kernel. But as part of that process, it will the firmware generally in the Dixie phase will do what's called registering SMI interrupt handlers, and it'll set up this system management RAM region and the protections around it. So there's essentially this carved out region in your main memory that the CPU enforces certain protections, where even when you're running in ring 0, essentially at the kernel mode, you can't read and write into this protected region. And all of the system management interrupt handlers are supposed to sit inside of this protected region of memory, and you're supposed to only be able to write it when the processor is operating in this special privileged system management mode.
You say supposed to, which I find hilarious.
Yeah, so it's supposed to work this way. There are some protections that, if the protections are not set up correctly, you can write to the system management region, because there's a value that's called SM base, which is a value in the processor, and when a system management interrupt is initiated and it does this mode change and starts executing code in this highly privileged system management mode, it looks for the start of that value at a hard-coded address above SM base. So it'll look at SM base and a particular offset and start executing code at that address, and it'll be running in this highly privileged mode. In addition to the SM base value, there is the protected range registers around that system management RAM, which is SMRR fizz base and SMRR fizz mask. You can misconfigure those values so that SM base points to a region that is not contained within that protected region. So the CPU will go enforce this SMRR fizz base fizz mask region, even though it'll execute code from where SM base points at. So there are some ways that you can misconfigure this, and
those, are those protected ranges for SMRAM like by default, or is that up to the OEM to set those?
That's what I was going to ask. Is that an OEM or BIOS specific?
Yeah. This is something that the SMRR fizz base is there's a mechanism in the CPU called a model specific register, and in order to read and write model specific registers, you need to be running in ring 0. There are some that have additional protections that you can only modify those when you are running in system management mode. But these SMRR fizz mask and fizz base are model specific registers that are initially configured by the UEFI firmware when it is initializing the memory map and setting things up. So it will, after you do basically hardware initialization and enumeration and figure out how much memory you have, one of the processes that the firmware is responsible for is doing things like configuring and locking some of these regions, and if it does that incorrectly, it could be unprotected, and then you could have a privilege escalation from ring 0 into system management mode. And you can also take advantage of vulnerabilities in system management mode in order to cause that desynchronization and cause that region to be unprotected by taking advantage of a vulnerability.
But all these things are intertwined. It's interesting. I want to talk about SMM vulnerabilities specifically, but I think what we've learned up to this point in Open Security Training 2, Zeno Kova has an Architecture 4021 Introductory UEFI. That's where I learned enough to almost understand everything Jesse's talking about. Not quite. So that's a great resource. So if you're lost, go to that first, then come back. But what we're getting to is UEFI sets up SMRAM, which loads code in there that are SMI handlers, and that can take other actions on the system and interface with hardware. And it's this reason that if I want to configure or secure something in the firmware of my laptop, let's say, that I have to go back to the manufacturer to do that, because there has to be code in there to read any configuration. Like if I change something on my SPI flash or change a register value, right? Just there has to be code in SMRAM in order to handle that. Pardon the pun.
Yeah, essentially, you're definitely describing this accurately. Where as part of the system boots up, the UEFI firmware will configure this system management RAM region. It will copy the code that will run as part of these system management interrupt handlers into that SMRAM region, and then because we want to protect that region, one of the things that has to happen before we transition and load the operating system is that region needs to be locked and protected, so we can't make additional changes to it. So one of the things that happens during that Dixie phase is different drivers will load and run as part of the boot process, and they will register system management interrupt handlers to do various different things that will persist into the runtime of the operating system. Usually it's for doing things like power control or other types of management tasks. There's a mechanism called UEFI variables, and the variable service is one of the runtime services that's handled by system management interrupt handlers. So there are some interesting things that you can do with variables and vulnerabilities that we can talk about in a little bit regarding that type of operation. But in general, the Dixie phase will copy system management interrupt handlers into SMRAM. At the end of the Dixie phase, it will lock the SMRAM region before it goes into the boot device selection and loads your operating system. So the intent is that the operating system should not be able to read and write into that region, but if it triggers a system management interrupt to basically request a service from one of these privileged interrupt handlers, there's certain things that it will go do at a more highly privileged mode than the operating system itself has.
Now, Jesse, you used the term driver, and It was interesting. I was actually talking about this with Mickey earlier. You weren't actually on that call. Most of the time you are, which is funny. I get to talk to Jesse and Mickey a lot, but we were talking about the overloaded usage of the term driver in this context. That when people read that, like UEFI is loading a driver, like you instantly think like a kernel driver for Linux or for Windows. But this is a different kind of driver. Mickey was kind of sort of okay with my description of it because I was like, well, UEFI is loading.
Well, let's let Jesse correct you.
Yeah, let's let Jesse describe it. So what is a Dixie driver execution environment, right?
Yeah, so one of the interesting things that they did, so with the old school BIOS, legacy BIOS, a lot of it was written in assembly, and it was kind of a mess of spaghetti code. And when they moved to this modern UEFI environment and the specification, one of the things that they did is they made this very modular environment. And there's a lot of things where code can load and run with a uniform format. It can then provide a service that is then used by something else. So you could have literally like what you would see in an operating system where you have a driver for a specific type of file system. Mm-hmm. Like you might have a FAT file system driver or an NTFS file system driver, or a driver for a particular type of network card or a particular type of storage device. And these will basically load, register themselves as providing a particular service, and then it'll exit and continue on, and then something else can look up that service and then make calls to it. So there's a mechanism that these different executables use. It's called a protocol and a protocol interface. And the protocols are defined by GUID. So each driver that you're loading is basically loading and running, and it might register a protocol with a particular GUID that then something else will then do a locate protocol and then call functions within that previously loaded driver. And it is different than a Windows or Linux driver, but it's a similar type of concept where you have some functionality that's being provided by an additional piece of code.
Does the kernel drivers interface with the GUID in the stuff that was loaded by the Dixie driver? Because I kind of think of it as it's like the initial driver that initializes the hardware so that other software later on can interface with it.
Yeah, so there's different levels of functionality that can be provided where, like in Windows or Linux, you can have like what's called a filter driver or something that provides hardware level access. And there are different drivers that provide that type of functionality within the UEFI environment. You actually also have a complete network stack, including like a TCP driver or a DNS driver that you can then call functions and services within that driver. One thing also to know about the UEFI environment is that even if you have a multi-core system, UEFI runs single-threaded, and there isn't strong memory protection between different executables that we think of when we're running in the boot process. So it's essentially loading a set of callbacks into your address space and then being able to find those callbacks in order to call functionality that was provided by this driver. So it is you could think of it as like an object-oriented programming environment in some sense, but a lot of it is just this particular driver runs during the boot process and registers itself as providing additional capabilities that are then used by different parts of the boot process later. So like you might have sorry go ahead
Tyler.
Are those drivers and within inside of that environment, the Dixie loading process, are there protections and validations, and is that coming from the TPM into the SMM, or how is that integrity and those drivers validated for the functionality that they're providing?
So I did mention secure boot. When the system is booting up, the code starts running at the reset vector. It just starts executing code, and during part of that process, it'll do things like register security handlers that will then be called in order to do things like when a new executable is loaded, it will do a cryptographic security verification on that executable. If it fails, there is a public key that's stored as part of the system. I mentioned UEFI variables. There is a key hierarchy that's stored in the UEFI variables, where there's a platform key, a key exchange key, and then DB and DBX are essentially an allow list and a deny list for this secure boot key mechanism. So when the system is booting up, it'll use this key hierarchy and look and see, is this code that I'm about to run, has it been signed by a public key that is in the DB variable?
And sorry, Jesse, it does that check for DXE drivers?
Yeah, so it depends on the policy for the firmware.
There it is. It depends.
There's the first. It depends. So
I love it.
Okay.
So yeah, there is a policy to say.
Go for it.
Yeah.
Sorry. So Josh,
when the system.
All right.
Sorry, was there a question there?
I really wanted the policy on the firmware part explained, because that to me is a fascinating. It depends.
Yeah. So when the system is booting up, there's another thing to understand here is that there's a long supply chain where multiple people provide code that all runs in this process, where there's the reference code that is provided by Tiano Core, that's then taken by independent BIOS vendors who add and modify things, and then that goes to OEMs who add and modify things before it actually shows up in your laptop. One of the things in the Tiano Core reference implementation is there's a mechanism for determining whether to do a signature verification based on where it's loading the executable from, and some of those can be, if you're loading from the SPI flash itself, there are some structures in the SPI flash on your motherboard called firmware volumes, and there's basically a value that says, should I check the signature on things that are in firmware volumes? And there's another policy value for, should I check the signature on things that are from fixed media, like a hard drive? There's another policy value for, should I check signatures for things that are coming from removable media, like a flash drive? And there's another policy value for, should I check signatures for things that are from option ROMs? Option ROMs are kind of an interesting case where it's more common in like a server environment, but essentially there's a mechanism where you can have a PCI card that you insert into a server or desktop, or even like a M2 slot in a laptop, where it's built into the PCI specification that this card can have some additional code that runs as part of the boot process. And in a modern environment with UEFI, that can be signed, but there's this policy that determines whether to actually check the signature or not. And there have been
Jesse,
some.
I'm sorry. The firmware volumes that dictate this stuff are in the BIOS region of the SPI flash.
So let me explain firmware volumes a little bit better. I kind of glossed over that. So within the SPI flash on the motherboard, there is the first part of the region. The first part of the SPI flash is called the flash descriptor, and it has what's basically a map of additional regions within the SPI contents. You might have an 8 meg, a 16, 32 meg SPI chip on the motherboard, which is your non-volatile storage for the firmware. The first region is the flash descriptor. It describes a map of where the regions start and end. And then there's also a permission region, which says if you have read and write access to each of these regions, and if the CPU has read-write, if the Intel ME has read-write access, if the gigabit controller has read-write access, things like that. But it's primarily just letting us know what the regions are, and one of those regions is called the BIOS region. The BIOS region contains the actual code that's run by the CPU when the system is booting up, and contains the code that runs during those phases that we mentioned. Instead of just having a complete blob of arbitrary code, there is some structure to that BIOS region, and there's something called a firmware volume, which is, you could think of it almost as like a file system within the SPI flash, where you can have a hierarchy, where you can have a firmware volume that contains other firmware volumes that contain additional files, including executables that run in the boot process.
And the NVRAM is a separate kind of sub-region within the BIOS region?
Yes. Yeah. Within the BIOS region, there's something called the NVRAM region, which contains the values for those UEFI variables. And the UEFI variables themselves also have attributes which define the permissions for when they can be read and written. And one of those is this variable something that is accessible during boot time? So there's a boot services attribute. There's also a runtime services attribute. And there have been some vulnerabilities where configuration of that policy that I just mentioned was actually stored in a variable that had the boot service, the non-volatile variable flag, which means that it is something that's stored in that NVRAM region, and also the runtime service runtime attribute, which means that the operating system can request to change that variable content at runtime.
Oh, was
so
that Yuri's? That was Yuri's Windows 8 disable secure boot talk. Like
yeah,
back in the day?
that was one of Yuri's bugs from quite a while ago, where there was basically a variable called setup that several of the bytes within that setup variable, you could just write zeros to those, and it would still claim that secure boot was turned on, but it wasn't actually checking the signatures of things like bootloaders that were loaded from your hard drive or from a flash drive.
And that's because all of these permissions that we talked about across the regions and the SPI flash, someone got them wrong.
Yeah. So that basically was the attribute for that variable was something that was marked as writable at runtime, even though it had critical configuration information in it.
Now, is that a mistake on the chip manufacturer and the spec in which they released for that function in that code, or is that the OEM and they're taking of a library for that function of that code and releasing it as code on the hardware?
So the CPU manufacturer has like a spec to say, do these different things. There's a BIOS writer's guide that says you need to configure these things these different ways. But the IBVs, independent BIOS vendors, and OEMs were not always following that guidance that Intel and AMD were providing. So we ran into cases where these configurations were not done properly, and this was generally like the OEM had misconfigured how this was supposed to be implemented.
Is this a good point to talk about Lenovo's drivers? Because I think I think a lot. I think people, including myself at first, read that wrong until I talked to people like you and Mickey, like my coworkers, and I'm like, wait a minute. They were essentially able to. So Lenovo has like 3 CVEs for drivers, and a lot of the popular press actually wrote it up as like drivers, and people would read that and go, "Oh, you mean like a Windows driver?" Like, no. They could mean a DXE driver that was included that would allow you to manipulate UEFI variables to impact secure boot. Is that essentially the high level?
Right. Yeah. So the most recent one that I think you're referring to is there were a few variables that. So I mentioned there's the reference code and the reference implementation. There are a number of variables that are defined in the specification and the reference implementation, and then IBVs and OEMs do their own thing on top of that. And one of the things that Lenovo had done is they had some special code looking for a few specific variables with specific variable names that you could literally just set one of these variables and it would turn off secure boot for you. So it seemed like it was a poorly thought out feature, but that was kind of an interesting vulnerability. But yeah, as you mentioned, there is kind of this overload between Windows drivers, which have their own security issues and vulnerabilities, versus Dixie drivers, which run during that driver execution phase in UEFI. we talked a little bit about the variables, and there are operating system mechanisms for adding new variables, modifying existing variables that have that runtime attribute permission. So like Windows has an API to get and set variables. Linux, if you look in the sysfs, there's a EFI variables directory that you can modify variables that way as well. But one thing that you could do, because you can modify some of these variables, when the system boots up the next time, you might have a bug in one of these executables that's running during the boot process in how it reads and parses the variable content. So you could have an instance where from the operating system, I can modify a variable, reboot the system, and exploit a parser bug in a Dixie driver that's running during the boot process when it does a get variable and tries to do some operation on the contents of that variable.
Oh, and I feel like there's a function call that a lot of bug hunters look for in Dixie drivers to like get parse variable or something. I've seen like the same variable name, which is, I think the function call is doing exactly what you described.
Yeah, so there's a variable, or there's a function called get variable, and this is also something that we run into in SMM vulnerabilities. We could probably talk about SMI vulnerabilities also while we're in the call, but
let's do it.
A lot of times there are these mechanisms to do a get variable, and then if they're not handling if the value that's in the variable is not what they expect, maybe it's too large, there could be a case that the code that's calling this get variable function isn't managing its own buffer properly, and it basically reads the full size of the variable into a fixed size buffer. So we have what's essentially a classical buffer overflow, except during the Dixie phase, or more dangerously in system management mode.
Yeah, so but to update, that was my question, to update variables that are set to be updated, read and written from the operating system, does the CPU have to be in system management mode?
So we mentioned that the NVRAM region is inside of the BIOS region. One of the things that the system is supposed to do when it's booting up is configure protection of the SPI contents itself. When the system boots up, there's essentially the SPI chip on the motherboard is connected to the chipset or platform controller hub in Intel terms, and there's a PCI device inside of the chipset that provides access to the SPI contents and does things like map the contents of the BIOS region at particular addresses like the reset vector so the system can boot. But when the system first boots up, you have the ability to write to the SPI contents, because we have to do things like maybe there's a bug in the firmware and we need to update that. So when the system boots up, the SPI is writable. Before it loads the operating system and runs and transfers control to the operating system, the firmware is supposed to lock the SPI controller, and basically there's some bits in the PCI SPI controller called the BIOS control register.
Josh. Is that the flash lockdown bit?
So yeah, there is a flash lockdown bit. There are some other bits inside the BIOS control register that you need to set as well.
They're dependent on your chipset. Like, make sure you read the data sheet for that chipset. As I found out when I was running, I was like, oh, there's lots of differences. Yeah, Josh, question. Hold on.
I have sort of a meta question. I feel like, and I think Tyler called it, I feel like a first grader having social studies explained to me. Like, I am blown away, and I have a question for you. How many more levels of detail do you have up your sleeve on this topic? Because I'm honestly curious.
Days worth of training.
Probably a few. I mean, so I mentioned like the rings and permissions there, virtualization. System management mode also has the ability to run virtualization inside of SMM, and there's some interesting protection mechanisms.
Way.
So yeah, so there's a mechanism.
Well, and we haven't.
There's a mechanism for system management. So The reason that they've tried to do this is some of the classic system management interrupt handler bugs that we can talk about as well, is because the system management interrupt handler is very highly privileged, and there have been a number of vulnerabilities in those. There was a mechanism to try and deprivilege system management interrupt handlers to only the things that so they could only access the resources they really need. So there's what's called a SMI Transfer Monitor, STM, that was created by Intel. I believe some vendors are starting to try and use that. I think the Microsoft Secured Core PC might be using STM as well to deprivilege the system management interrupt handlers. But yeah, there are a lot of very complex interactions that are happening in the system. So one of the classic types of vulnerabilities that we'll see in a system management interrupt handler is that I mentioned that all of the code that runs as part of the system management interrupt handler needs to reside inside of that protected SMRAM region, because if the code that's running as even the kernel ring 0 has the ability to modify that and then can trigger code that runs that it modified, that would be a privilege escalation from ring 0 into SMM. And one of the classic vulnerabilities in system management mode is what's called an SMM callout, where you call a system management interrupt handler, it goes and does something, and then it calls code outside of that protected SMRAM region. So there are a lot of vulnerabilities where a system management interrupt handler incorrectly calls something from what's called the boot services table, which was a table that is outside of SMRAM that is used during the Dixie phase and PEI phase, or during the Dixie phase and the boot device selection phase, but it's outside of SMRAM.
Yeah,
so
I mean, it's not bad. I mean, 48 minutes, and we got like just enough information to understand some of the vulnerabilities we talked about on previous shows that were SMM called. That's why I was telling everyone, I'm like, SMM called. Like, I need Jesse to explain it.
You realize that Jesse and Paul, your company, I hate and love, and I hate because you've just like on open air gone. By the way, the world of security is 3 continents bigger than you thought.
Yeah.
And nobody knows what the fuck is in there.
Oh, yeah.
And it's full of tigers and dragons. Literally, there be dragons there is on the map for those fucking places.
And you are crunchy and taste good with ketchup.
But like I told you, Josh,
and I love you guys because you've just given us job security for 20 fucking years.
Like the time you push the power button on your computer to the time you see a login screen, it's astonishing how much is happening. And Jesse, you've given us some insights into some of those lower level bits that
and you can have things running on the system before you even press the power button. So
yeah, this is true. We haven't even talked about ME or AMT.
So I have what's perhaps a silly question, but and it's a 2-part question. I'm a user of laptops, and both work and personal, and let's say I'm an admin of such types of systems. What am I supposed to be doing about all this?
Are you jumping right to the solution?
Yeah. So one issue is just the visibility into some of these low-level components has not historically been great. That's actually one of the reasons that our company got started, is because there were a lot of OEMs that were not configuring the hardware correctly and not protecting things, and nobody was really looking at the firmware itself and the UEFI code that runs. This you could potentially have like 300, maybe 700 individual executables that run as part of your boot process, or could potentially run as part of the boot process on a modern laptop or server, and nobody was really looking at this. We did. There is a open source tool called ChipSec that Yuri, one of the founders, originally created when he was at Intel. I've contributed to that also. It's a good way that you can kind of explore the system and test, kind of look at some of these interfaces and do things like dump the SPI contents, extract all the SPI contents, extract the firmware volumes into these individual executables. One thing that's actually really nice about UEFI in general is that when they design the specification, these individual executables do use, it's essentially a slightly modified version of the Windows PE format. So a lot of the reverse engineering tools work, and you can load these. They do have a different calling convention for the entry point, and like you don't have like the same sort of libraries that you would have in Windows or but it is a PE executable with just a different subsystem value.
And Jesse,
so you can
Linux
take a closer look at that.
Linux zealots hate the fact that it's based on a Windows PE. By the way, I heard some complaints about that recently, some rants.
Yeah.
But my blog post, just my blog post series walks you through a lot of the chipsec stuff in addition to my presentation that I mentioned for that I gave for BHIS. Talks about chipsec and how to go discover this stuff. Some of this, well, there's more because we haven't really talked about Intel ME, which is another. We'll have to bring Jesse back for that, but yeah.
Yeah. So there is a lot of issues that you can have with, like I mentioned, SMM callouts. Another thing is, like as we've seen in like operating system and application exploitation, you can have what's called a confused deputy, where you can do things and it will go do things for you on its behalf with higher privileges. One of the types of things that we see in system management interrupt handlers is what's called a read what where primitive, where you basically pass an address and it will then do a write to that value for you, or maybe there's some way that you could get it to write a 0 to a particular address for you with that higher privilege, and there are some ways that you can take advantage of that. That's another
Speed Racer.
Another pretty useful one. So Speed Racer was a pretty interesting vulnerability related to how the interaction with the SPI controller and the protections there. I mentioned that when the system boots up, you're supposed to set certain values to lock the SPI controller to protect the BIOS control or the BIOS region. And then once those values have been locked, they can't be unlocked until you do what's called a platform reset, reboot the system. Then they get unlocked again. The system runs the UEFI firmware again. But the goal is that once these values have been locked and the protections are in place, the only way to write to the SPI contents is when the processor is running in system management mode. So that's another reason that we have things like the variable service. And there's a mechanism in system management or in UEFI runtime services called update capsule, which is it's a mechanism for doing updates to the UEFI firmware itself. And part of that involves running these system management interrupt handlers in order to do updates to the system. If you want to read and write one of these non-volatile variables that's in the NVRAM region inside of the BIOS region, the code needs to be running in system management mode in order to actually be able to write to the data on the SPI chip itself. So when you call the OS API in Windows to say set variable, it will then trigger a system management interrupt, which then runs this basically this set variable code in system management mode, which then allows it to bypass the SPI protections and actually modify the value in the chip on the motherboard. So there's a lot of mechanisms there, and that's the intended way that you're supposed to be using this functionality. But if we have a vulnerability like a write what where primitive in SMM, or like an SMM callout, there are ways to run arbitrary code inside of SMM, and because the operating system doesn't have the ability to look inside of SMRAM, you can do things like have a system management mode rootkit that can sit there and be more privileged than the operating system and subvert operating system security controls. There are some proof of concept SMM bootkits or SMM rootkits that will do things like from a normal user mode unprivileged application in Windows, you can trigger a system management mode and it will elevate the privilege of the applications running currently and triggering that. So, and that's something that is bypassing the Windows kernel itself. And you can have code that runs in system management mode to scan through Windows data structures and modify things in memory that the system or the Windows kernel doesn't really have the ability to prevent that from happening because it's running in a more privileged mode than the processor
right.
or than
it trusts the
kernel
previous
itself.
the previous rings. Mandy, you had a question.
I did. I actually have a couple. But first, I want to tell Jesse, like, kind of what the other hosts are saying, that I feel like I've stepped into Narnia, and it's kind of gorgeous. So thank you for how you're explaining everything. My first question, I want to go back to the virtualization. Was it in the SMM?
Yeah.
Okay. When did that become possible?
There's just the general virtualization hardware that we see that's normally used for running VMs like vSphere, VMware, VirtualBox, whatever. But that same physical hardware in the CPU exists and can be activated in SMM also. It is something that you generally have to have the OEM build into their system management environment when the system is booting up. You might be able to do something crazy and take advantage of a SMI vulnerability in order to inject your own code to do some weird virtualization things in system management mode. But the intent of this STM, that's what it was. SMI Transfer Monitor is the Intel code that was an implementation of using this to deprivilege SMI handlers. There's actually a pretty good presentation. I think it was at the Open Source Firmware Conference about STM and how that works and the design goals of why they were implementing this. But the idea is that if we have these vulnerabilities and we're having issues where OEMs are adding new code to do special things for their specific use case, we're going to have things like these callouts and arbitrary write primitives, information leaks, other memory corruptions within SMM. If we can essentially have a hypervisor inside of SMM that then runs the individual system management interrupt handlers as guests, we can deprivilege those and basically restrict the resources that they can access to the only things that they're intended to access. So you might have a SMI handler that's doing that variable update service, and if you know that should only talk to the SPI controller in order to do reads and writes to the MVRAM region, and it shouldn't be able to talk to other parts of the system and modify the physical memory that the operating system kernel is sitting in, you can restrict the guest to only have those permissions. So that was kind of the design goal of how STM is supposed to work. Did that answer your question?
It did. I mean, I love that, but it's also, I wondered when, like, was there a particular time where that started becoming a possibility?
I think STM only came out a couple years ago. It's been a persistent issue for these SMI vulnerabilities. One other thing to be aware of is that more recent CPUs have a hardware mechanism. It's this. There's a SMM feature control MSR that contains a code check enable bit. That if this bit is enabled, and the code tries to do a call out and just natively jump to code outside of SMRAM, it will basically cause the processor to fault and it'll do a machine check, I believe. There are some ways that people have been able to bypass those. One of the things you can do is when the system transitions into system management mode by doing that SMM system management interrupt, there's something called the SMM save state area, where it basically saves the contents of all the registers at a particular fixed address within the system management RAM. So if you put some shellcode in the registers and then trigger a SMI interrupt, the value of those registers will be saved at a fixed location, and you could potentially jump to that and then disable that code check value and then jump outside. Or
also,
there's a mechanism.
Jesse, this gets, I think, starts to segue into when Jesse was explaining this to me. I was like, oh, this is why when I put my laptop to sleep and I wake it up, that stuff doesn't work anymore. Like historically, I think everyone who's a techie user, right, even non-techie users, like, I just want to use my laptop for work. Explain this to like my soccer parent friends. They're like, oh yeah, that happens to me like all the time. It's because the stuff you're talking about, right, the SMI handlers and NVRAM variables, when your machine goes to sleep, like it stores them. And is that when it does the platform reset is also on wake from sleep?
So there's something really interesting about how the sleep states and the sleep process works. So when the system boots up normally, we have this long process of device enumeration and running all this code in order to set up the system and run things. When the system goes into sleep states, there's something called an S3 BootScript.
Yes.
That we don't want to do all the same long configuration. We want to have basically a fast path or a shortcut to that. So when the system is doing that initial slow, long boot process, it's also building something that's called the S3 BootScript. And that contains critical register configuration and device configuration for when the system comes up. So when it comes out of reset and is waking back up, or when the system is waking back up, it basically, the processor is coming out of reset and it goes through this fast sleep resume process where all of the hardware configuration registers have been reset to their default value, and we want to go and basically run this S3 BootScript in order to go set all the values that have been stored from the previous long boot, the long slow boot process. There have been some really interesting vulnerabilities where not all of the configuration values that were set when the system initially booted up were stored into that S3 BootScript, and you could basically, I think there were some
it was Apple.
Mac Apple vulnerabilities where you could just set the system to go to sleep and resume, and then a lot of things were there were some things that were unprotected, and you could exploit the system after just setting it to go to sleep and resume.
It was it SMM BIOS lock enabled, BLE or something? It was one of those bits that protected.
I think it was like one of the BIOS lock enable bits was not set properly. There also were some issues where that BootScript was stored in an unprotected region of memory, and you could just find it in memory, modify it, and then trigger a sleep and resume, and then basically unprotect everything.
Wow. And that's how malware goes deeper into your system and can get around the operating system. Any operating system protection, I think, is the one of the key takeaways, right?
Yeah, if you have SMI vulnerabilities that you can take advantage of and get code execution in SMM, you can basically bypass all the operating system protections that are running.
That's awesome. And so we covered some this was relevant to some things we covered when I talked about DXE and variable, basically buffer overflows when the DXE driver reads a variable. We covered some of those that have been disclosed recently. The recent Lenovo ones, we talked about the UEFI variables and being able to control those in that vector. SMM callouts, now we have a better understanding of how those work. Those are some pretty major bug classes, I feel like, Jesse, they're all in UEFI.
Yeah. So another thing to understand about UEFI is that, like, if you're familiar with operating system and application level exploitation and exploit mitigation defenses, you'll know about things like address randomization, non-executable stack, non-executable heap, things like that. Maybe stack canaries. If you're looking at the UEFI environment, we're quite a bit behind the state of the art that we have in application level and kernel level things, because most systems won't have things like stack canaries when it's running in Dixie or SMM. You'll basically have an executable stack. You'll have an executable heap, things will be loading at mostly predictable addresses. So it's a lot easier to take advantage of things like a classic buffer overflow in a UEFI environment than if you're exploiting like the latest version of Chrome or whatever.
Sure, but you have to read all and understand all 3,000 pages of the UEFI specification.
Maybe. I mean, you can find some things like, oh yeah, this is way easier than I expected.
Yeah, or we could just ask Jesse.
Or my shortcut is I just go ask Jesse.
Because based on
so as an end user, though, is there anything that we can do for some of these vulnerabilities? A lot of this relies on the hardware vendors, the OEM vendors, and the implementation of both their BIOS and UEFI implementation, as well as their ability to update and patch those things like SMM or firmware. So is there things that we can do as end users in order to secure our systems better and to mitigate or prevent some of this?
Yeah, I mean, like I did mention the chipsec tool. Like the company that we started has our own product to basically do this kind of device configuration and integrity verification. There is the ability to dump the contents of the BIOS region, and then you can do an evaluation, check and see if there's something there that you don't expect. You can download the version of firmware from your vendor for your particular device and compare and see if there is a difference between the version of firmware that your device claims that it is and what is actually in the BIOS region.
Oh, but that's a great point, Jesse. So, with the Lenovo case, though, that we talked about, there was one model laptop where Lenovo's like, it's end of life. We're not going to give you a firmware update for that. And like, I don't want to knock manufacturers, right? Because like it's a very costly process, and I think it's an unfair expectation to say everything that you bring to market you have to support forever. Like there has to be a cutoff at some point. Yeah. But if you have one of those laptops, what you were saying is you got to look at what you have and check to see if it changes, right?
Yeah, I mean definitely if there is an update available. Yeah. And you can get that from the vendor, but yeah, if you have an older system, you might have an old Windows XP system in a production environment somewhere, which is kind of terrifying for other reasons. But but yeah, I mean, there's a lot of cases where the computer still works, but the vendor is no longer providing security updates for that particular platform, and for some of these types of things, there isn't really a good mechanism for fixing it yourself. There are some things you can do as far as monitoring the system and like looking to see if you have changes that you don't expect or something that's in the firmware that you don't expect. Like I mentioned, there's chipsec that can do some evaluation of some of those protections, like the BIOS control register, seeing if it's set up properly. There's our product, of course, but there's different ways that you can kind of explore and check some of the configuration of are some of these things set up properly. One of the problems is knowing what to look for. Like you mentioned, there's multiple generations of hardware, and just within the SPI controller, they've had different sets of protection bits that are required to set to actually configure things properly, where maybe a Sandy Bridge system from 2011, you needed to set up the SPI controller protections a certain way, and then a Skylake system, there's maybe an extra protection bit that you need to also know about and make sure that's set up
and
also.
Then there's dependencies on each other, and you end up with this graph of like, if you set this bit but not this bit, you're vulnerable in this way, but if you set both those bits in this other bit, you're vulnerable a different way. Like it gets really...
Yeah, I mean, there are some redundant protections, like there are protections just for the BIOS region itself, and then there's also what's called protected range registers, which can be more granular and protect portions of the BIOS region, and say you only have read access or you only have write access to this particular region, but not the rest of the BIOS control region. So there are some overlapping protections that can, maybe if you're using one, you don't need to use the other, but it's good to know how these actually interact and what some of the mechanisms that things like sleep states, where if you go to sleep, you need to make sure that those protections are still set properly when it wakes up again.
Mandy, did you have one last question?
Yes, thank you. So going back to kind of a broader view for you, Jesse, when going to UEFI from EFI or even from BIOS before, what were like one of the top 3 things in the enhanced flexibility that made you the most excited?
I mean, just having a security mechanism like Secure Boot in the first place, like it basically helps us know that the code that we're running is what we expect to some extent. There are some limitations with Secure Boot. There actually is something called Boot Guard that helps protect against that. But in general, once the system is booted up and the code is running and checking signatures, the policy is set correctly, you at least have some integrity protection that you are running what you think you're running. And there are some ways that you can bypass Secure Boot, but I think that's a good mechanism. It doesn't guarantee that the code is bug free.
You and Mickey found a few ways to bypass Secure Boot.
Yes, yeah. So we did give a pretty fun talk at DEF CON this year. That was one bootloader to load them all. Basically talked about 3 bootloaders that are signed by Microsoft, and one of them in particular had a very easy Secure Boot bypass. It basically would load another module with a known name and run whatever unsigned code you wanted. So you could just load and run that, and it was essentially unintentional Secure Boot bypass for this third-party.
I mean, that's similar
application.
to SMM callout, right? Kind of along the same lines.
Kind of, yeah. I mean, it's essentially you have this security mechanism that is trying to protect the system, but then there's code that is intentionally running. They basically implemented their own code to load and run this unsigned code rather than using the built-in UEFI load image, start image functions that would have done the security.
Similar. I know we're running long on time, but now you bring it up when you load the Linux kernel and all of that code is signed and trusted, and then it wants to load init-rd, and it was the guy. Did you read this article? I don't know if I sent it to you or not, Jesse, but I might have sent it to John Lucades. But there was the guy that wrote System D that works for some Linux company like SUSE or something. I forget which one he were, Fedora or something like that. And he was saying we should incorporate init-rd, which is that temporary RAM space that the kernel creates to like basically load other stuff in this kind of the same context that we're talking about, just later in the boot phases of what we were just discussing, and that should be protected as well. But if it's not, you could get trusted code to basically load untrusted code.
Oh yeah, definitely. I mean, like that's a friend of mine actually gave a talk about this type of rootkit. Horse pill was the talk about basically putting rootkits in init-rds and doing some funny games with some of the path manipulation and some things that you could do there. So there's some container mechanisms that are in Linux that can be used for having like an alternate root and doing some different namespace things that he took advantage of. But yeah, like one of the issues is like you have the UEFI firmware loads your bootloader, which might be the shim for Linux. The shim will then load and verify grub. Grub will then load and verify the kernel. The kernel will then load the init-rd, but there's not all of the verification that we would like to have is happening with the init-rd. So you could potentially put a bootkit in there. There have been some efforts to do signature verification on the init-rd also, but
and there's
I'm not sure
unified kernel image. Unified kernel image is what we were talking about last week to put that all in the same Windows PE or same. I think it was right. Putting it all in one file that gets verified basically was what he was talking about, a very high level.
Cool.
Awesome. Jesse, we have to bring you back because like we didn't talk about, I mean, we touched on secure boot stuff. Larry, you have one question?
No, we have the 5 questions.
Oh, we have
5 more questions.
We have to ask you the 5 questions.
Paul's going to find
wait, did I ask you guys the 5 questions when you were on before talking about the bootloader stuff or no?
I don't remember.
So that would be no.
That would be.
Let's say no.
I have to. All right, you ready to play 5 questions with Security Weekly?
Sure.
All right, 3 words to describe yourself.
I mean, I'm kind of a dork.
That's a term of endearment.
That's
Yeah.
one word. We need 2 more.
Dork.
Dork.
Word.
Dork, dork, dork.
I'm old. I mentioned that already. So
Old dork. One more.
I don't know.
Biker.
Yeah, I
Musician.
do.
I
Have
love your
multiple
shirt.
motorcycles.
Yeah, I can see the full shirt. I love the shirt. Jesse, if you were a serial killer, what would be your weapon of choice?
Maybe poison.
If you wrote a book about yourself, what would the title be?
I don't have any idea what I'm doing.
What is your favorite hacker movie?
Probably sneakers.
Oh,
Yay!
Jeff wins that one. Jeff and I have this
Yay.
wager going. I'm in the hackers camp. Jeff is in the sneakers camp. So Jeff scores this point.
You're my new best friend.
Jesse, choose 2 celebrities to be your parents.
Alive, dead, fictional, or otherwise.
I mean, Einstein and maybe Ada Lovelace.
Jesse,
I felt like he was going to say
I
that.
felt like he was going to say that too. I felt that. I felt the disturbance in the
It was either that or Angelina Jolie.
Yeah. Yeah.
I mean, that too.
Or Betty White. I wasn't sure it was going to go like Betty White or Ada Lovelace. Yeah. Jesse, thank you so much for reappearing, actually, solo this time on Paul Security Weekly.
No, thanks for having me.
Thank you.